So this would be dy dx equals negative 21 times in brackets 5 minus 3x close brackets raised to the 6. I know that we did spend some time on Thursday going over some of the problems from the textbook, and many of you had questions, but let's just put on the brakes here and stop for a second and ask again if anybody has any questions from 1 or 6 before we move on today. Arden? 6i. 6i? So we have, and this is a good one from a standpoint of applying rules. I'm going to take the liberty of rewriting that as x squared minus 1 over x squared plus 1 raised to an exponent of 1/2. I know where many of your minds go, and it's, would this be on the exam? And the answer is yes, it could be on the exam. Okay. We're doing this question and basically all of these because you never know what could be on the exam, but we're also doing them. Don't lose sight of the fact that I'm trying to get you better at math and prepare you for post-secondary. When I look at the big picture here, Arden, this is a power. A power is a base raised to an exponent, and that's the big picture. So I have to apply the power rule, which means I'm going to wrap that exponent of the power around the base of the power. The base stays the same. That's what the power rule says, is you wrap it around the base and the base is the same. You drop 1 from the exponent, so the exponent was 1/2, and now we take 1 minus, or 1 away from 1/2, and we will get negative 1/2. But then the chain rule says we have to multiply by the derivative of what we wrap that exponent around. So now I have to multiply by the derivative of this, and I look at that thing and I say, well, that thing is a quotient. And it's all rule oriented. You don't want to get ahead of yourself and just say, I'm going to differentiate the top and differentiate the bottom. It's a quotient. To differentiate the quotient, you have to use the quotient rule, which says I'm going to take the derivative of the top and multiply by the bottom, and then I subtract the top multiplied by the derivative of the bottom, and then I have to divide by the bottom squared. And I will double check that in a second, but I believe, everybody, that this next little bit of business that I'll mention is important. When you are using the chain rule, and in this case multiplying by the derivative of what's inside, you really want to not look at anything else. You only want to look at what's inside. I mean, I'm not saying you erase things. That's not the way to go. But it's very easy when you're multiplying with the chain rule by the derivative of what's inside to start including the half again or the negative 1/2 again or something like that. That's not what we want to do. So this is the derivative of the top of that highlighted blue section, and it looks fine. This is the bottom. The quotient rule says minus the top, which is fine, times the derivative of the bottom, which is fine, over the bottom squared. Are you okay with that, Arden? Okay. So now what we want to do is clean this up as much as we can. We have two things that we have to consider here. Well, two things that jump out at me. One, we have a negative exponent, and I can clean up that negative exponent by simply doing the following. And I want to talk about that. It's not a complicated thing, and I hope most of you see exactly what's going on here. But if I just take a break away from this for a second, you're taught in, I guess grade 10 is the place it's introduced, that if you have a base raised to a negative exponent, that can be rewritten with a positive exponent by writing 1 over that power with a positive exponent instead. So what happens if you have a fraction raised to a negative exponent is you end up with 1 over that fraction raised to the positive exponent. And I'm going to kind of go in circles here to demonstrate my point. What I can then do is apply that exponent to the numerator and denominator of this fraction of m over n. Oh boy, I really shouldn't have used n. I'm going to change this n to a p. I don't want two n's. Okay. I think you probably get the point anyway, but I don't want to cause any undue confusion. So m over p to the negative exponent is equal to 1 over m over p to the positive exponent, and I can apply that exponent to the numerator and denominator, which is kind of it's called a power of a quotient, or power of a quotient. It's a grade 9, 10 thing you learn. But then, your grade 9 and 10 teacher, and maybe your grade 11 teacher would say, let's multiply by the reciprocal because you're dividing by a fraction. I would prefer to say at this point in time, let's just multiply the top and the bottom by this pesky denominator here to get rid of it. Anyway, I get p to the n over m to the n. And what we learn is that we can adjust our rule on the left that says we can do that to a new rule that says if we have a fraction, let's just flip the fraction over. So I want to be clear here, Arden, and everybody. I'm not suggesting that you do all this work to flip it over. I'm just pointing out to you that's what I did here. I took that base as a fraction that's in blue and I flipped it over to a new base. The other thing I want to do is, and maybe it's best to just think of this other piece here as being the result of the quotient rule, which it is, but just imagine that's all you were doing. What you would do then is you would factor out a greatest common factor out of these two terms that are being subtracted. And I can see I can take out 2x. And I would have left out of the first factor, I would have left the x squared plus 1 minus out of the second factor, I would have the x squared minus 1, which of course it's important for you to put that x squared minus 1 in brackets because you're subtracting it, right? And you have to subtract the entire thing. This is now over the x squared plus 1 quantity squared. Are you okay with that step, Arden? Okay. Now, one of the things to understand here is that there's a line running through this whole thing. What do I mean by that? I mean, it's one big fraction. It's times, times, times everywhere. I can think of this piece here as being x squared plus 1 to the half over x squared plus 1, over x squared minus 1 to the half. But ultimately it's being multiplied by the 1 on the top and the 2 on the bottom. I'm multiplying by a 2x on the top. I'm multiplying by a 2 on the top. From here to here is 2 because x squared minus x squared is 0, and then we have 1 minus negative 1, which is 2. And on the bottom I also have x squared minus 1 squared. So what I'm getting at here is this is really one rational expression where what we have is a series of factors on the top and a series of factors on the bottom. And as you know, anything goes with regards to canceling if it's like this. In other words, if there's a factor on the top identical to a factor on the bottom, you can cancel. That's all I can cancel for numbers. I do want to simplify, and I made a mistake here. This is positive, isn't it? I do want to simplify. Let me just highlight that correction to the mistake in case somebody's watching this on video later. That is definitely a plus. I do want to simplify this because what I have on the top of this expression is this base raised to a half, and on the bottom I have that base raised to the 2. So, we can make this simpler by saying, what if it were, instead of that blue to the half over the blue to the 2, what if it were a to the half over a to the 2? Can we simplify that? Well, yeah. There's a number of ways to do it. I'm just curious, by a show of hands, how many of you think of this in terms of canceling and getting a to the 3 halves on the bottom? So you're saying that, well, I can get rid of a half, an exponent of a half on the top and the bottom. The other thing to do is to say, and this is from grade 9 and 10, when you divide common bases, you take the numerator exponent minus the denominator exponent. So when you take 1/2 minus 2, you get negative 3/2, which means that's equal to negative 3/2 over 1, but what we can do instead is write it in the denominator to a positive exponent of 3/2. Now, I didn't really lose track here, but there's a lot going on, so I want to double check everything. I've reduced the x squared plus 1's down to x squared plus 1 to the 3/2 in the denominator. The 2's are gone. I'm left with an additional 2 plus the x in the numerator, and then x squared minus 1 quantity squared. Follow all that? Okay. Yep.
Shouldn't the x squared minus 1 be to the half?
Oh, yeah. Thank you. This half was being distributed in here. Don't know what happened there. It should be to the half, definitely. Other questions? Let's just stick to the textbook first, then we can go to the handout. Any other questions? 1C, Demi? So we are looking at x cubed plus x squared minus 2 to the 3/4. And like many of the questions in this section, let me rewrite it first, and I'm going to use my favorite, which is y. Like many of the questions in this section, particularly question 1, it's not like we're going to go through all this detailed process to simplify the result. We're just applying the chain rule. So when I apply the chain rule to a power, I differentiate by wrapping that exponent. Better make sure I wrote the question down correctly. I did. By wrapping the exponent, which is 3/4, around the base, which is rewritten in identical form to what it was, and subtracting 1 from the exponent that was. So this number in here is going to be 3/4 minus 1, which is 3/4 minus 4/4, which is negative 1/4. And then I have to multiply by the derivative of this. And the derivative of that is going to be 3x squared plus 2x. And, you know, very similar, Demi and everybody, to the question we were just talking about. There's a line running through this. Everything is being multiplied on the top and the bottom of a fraction. What we actually have is this whole thing over 4. So because of that, because these things are being multiplied, I'm allowed to take that x squared plus, or pardon me, x cubed plus x squared minus 2 raised to the negative 1/4. Because it's being multiplied on both sides by everything else, I can dump it on the bottom with a positive exponent. That's the nature of factors. There's one other little thing I can do. Let me rewrite it just with that step. First of all, though, I have 3, then I have a 3x squared plus 2x. And then it's over 4, and it's also over x cubed plus x squared minus 2 raised to the 1/4. So I'll pause there, Demi. Does that make sense to that line? Good. There's one other thing you can do here, everybody, and the general rule is the more factored something can be, the better off it's going to be down the road for a use. The only real use you have for derivatives so far is finding slopes of tangents, but it gets more involved than that. And more factored is always better. So I can take out of this factor here, this is a factor, I can take out a factor of x and load that x, pair it up with the 3 and have x and have 3x plus 2. And this is over 4 times x cubed plus x squared minus 2 to the 1/4. It gets a little confusing because I'm seeing that 3 that was there already, so I have to kind of ignore that, right? Take out the x, it becomes 3x plus 2 in the brackets. Is that okay, Demi? Okay. By the way, factored is better because I can easily look at this now and I can tell that there are 2 values of x that make the derivative equal to 0. Negative 2/3 and 0. And that will be important for later. Let's move on now and take a look at the additional handout I provided you. And I don't want to spend too much time on this. We do have another lesson to get going on today, but I would be negligent if I just said don't worry about it. Questions, Marcel? Certainly. So we have b, which is 2 times x squared plus 3 quantity squared raised over x. For some of these answers, I'm not a real huge fan of how they're written. I didn't make this up. I pilfered it from someplace online. I found it. And some of the answers are maybe written in a bit of a weird way. So keep that in mind. Unless I am willing to FOIL out x squared plus 3 times x squared plus 3 and then multiply it all by 2, and then divide each term by the x in the denominator to avoid power rules and chain rules and all that, I have to use the quotient rule. And I'm here to tell you, if you do all that to avoid the quotient rule, you're going to be making more work for yourself. Because if you FOIL it all out, you need it to be factored in the end. So I'm going to use the quotient rule, which says f prime of x, one of the rare times I'll use this notation, will be the derivative of the top. So this is the top, and this is the bottom. And the quotient rule says that f prime of x will be the derivative of the top, which will be 4 times x squared plus 3 raised to the 1 times 2x. So let's just talk about that for a second. I've wrapped the exponent, I'm just looking at the top only, I've wrapped the exponent of 2 around the base of x squared plus 3. I've kept the base the same and dropped 1 from the exponent. So that number in front is 4 because the old coefficient times the exponent I wrapped around is 4. Then I multiply by the derivative of what's inside. So Marcel, are you fine with that step? Okay, now I have to multiply by the bottom, which is x. And then I'm going to subtract the top, which is 2 times x squared plus 3 quantity squared times the derivative of the bottom. And then before I forget, I have to divide by the bottom squared. Now I'm going to double check everything. This is the derivative of the top. Pardon me. This is the derivative of the top. Just double check that. 4 times x squared plus 3 to the 1 times 2x. That's the derivative of the top, and it's fine. Multiplied by the bottom, which is here, and that's good. Minus, that's correct. This is the top times the derivative of the bottom over the bottom squared. It looks fine to me. So you're okay with that? Okay. Now what I'm going to do is factor. With the product rule and the quotient rule, you are always going to end up getting 2 terms, right? In this case, with the quotient rule, you get a term minus a term. And each of these terms has a common factor of 2. And each of these terms also has a factor of x squared plus 3. There's x squared plus 3 in the first term. There's x squared plus 3 in the second term. We take raised to different exponents. We take out the lowest exponent. So I can factor out or remove from the numerator, not remove, but write it elsewhere, a 2 that I factor out and an x squared plus 3, and have left, well, what do I have left out of this whole thing here? I've taken out a 2, I've taken out the x squared plus 3, so I've removed this and I've removed that. I still have the 4, and I still have 2 x's multiplied together, which gives me 4x squared. Minus, what do I have out of the second term? Well, I've taken out the 2, and I've taken out one of these things. You know, the x squared plus 3 quantity squared doesn't have to be thought of as a square. It can be thought of as, x squared plus 3 times x squared plus 3. And I've removed 1, so I have 1 x squared plus 3 left. And again, when you're subtracting, you better put the thing you're subtracting in brackets, otherwise you're doomed. This is over x squared. I just want to double check that, and I often double check factoring by multiplying it in to make sure I get what I started off with. When I take the 2 times the x squared plus 3 times the 4x squared, I get 4 times x squared plus 3, and I get 2 times x squared. It's all there. When I multiply the 2 and the x squared plus 3 by the negative x squared plus 3 I've claimed is what's left, I'm left with negative 2 times x squared plus 3 quantity squared. So just to double check, and are you okay with that step? Okay. Now the golden rule is once you've factored out what you can, you simplify what's left inside. And in this case, what we have left inside is 4x squared minus x squared, which is 3x squared. And then I also have minus 3, and this is over x squared. And more factored is better. So I can factor, how many of you see how x squared, 3x squared minus 3 will factor? I'll take out the 3, and then I'll be left with the difference of squares. I can even go further. And that's really what you should do. I don't know what the creator of this did. Oh man, was this B? I wouldn't, remember at the beginning where I said you could FOIL it out and then divide everything by x and differentiate? That's what was done here. And this is a very bad thing that was done. Okay. Well, let's deal with it. This is an absolutely useless form of a derivative. Derivatives need to be expressed as a rational function, as factors in the numerator over the denominator. So what this really is 6 times x squared plus 12 minus 18 times x to the negative 2. That's what we have there. And really, whoever did this should be factoring and saying, well, I can take out a 6. I want to talk about this because I don't want you to be led to believe that this is a good idea. Multiplying it out to get that. I can also factor out x to the negative 2. And if you take a look at where we are at, I hope you see where the 6 is going to come from. And I hope you see why we get x squared on the bottom, because x to the negative 2 is x squared. Anyway, what do I have left? I have x to the positive 4. Just think about that for a second. What's essentially happened here is whoever made up the key multiplied stuff out into a polynomial-like form where you can't really see what the factors are. So we have some work to do to unwind that mess. This will be plus 2x squared, and this will be minus 3. Just think about that. This goes back to day 1 when we talked about adding exponents that we factored out to the exponents we have left. So x to the negative 2 times x to the 4 will be x to the positive 2. X to the negative 2 times x to the 2 will be x to the 0. X to the negative 2 times x to the 0 will be x to the negative 2. And it turns out that because they have multiplied it all out, they would then have to think of this degree 4 as being a weird kind of quadratic. And this goes back to Math 20 where you factor those things. And we actually reviewed a bit of that. And if you were to take a look at that and compare it to where we were at here, I hope I hope that you can see they really are the same thing. And as I said, you would even go even further and take the x squared minus 1 and factor it into x plus 1, x minus 1. I feel that was worthy of a discussion because this is a very bad habit to do that. If you look at D, D is fine. If you do that and you happen to get a nice quadratic, then that's okay. Anyway, have I helped you out? Okay. Any other questions? Arden?
Did you go up on the last
On the work?
Yeah, on the work.
The way I did it? Tell me when to stop. What are you wondering about?
Was it 2 x to the squared plus 3? Or, yeah, 2x squared plus 3 over 2. Was that on top?
So there's the top.
I'm just confused because we took, yeah, I'm just overthinking.
No, it's okay.
Took the derivative of the top minus
Times the bottom.
times the bottom. And then wait, I think I got it. I think I just switched it up because I did the derivative of the bottom first and then the top.
And you can't do that. Yeah, the quotient rule is order sensitive. You have to do derivative of the top times the bottom and then minus the top times the derivative of the bottom. And by the way, if any of you think you're alone when you're doing this and you're connecting the chain rule and the power rule and the quotient rule and you understand each of those 3 rules perfectly, if you think you're alone and getting confused when you put them together, you're not. Sometimes I'll be doing things and then I'll go, man, what did I just do? Did that make sense? Like, it really is easy to get caught into a mental trap. All right, we are going to move on now and take a look at the next lesson. We have 2 more lessons to go. One today, one tomorrow. We're reviewing for the rest of the week, and we're also reviewing Monday of next week. I have so much flexibility in teaching this course that we can find time for things like review because it's very important. Our unit exam is scheduled for Tuesday if the lockdown drill is in the morning. So if you are in a class in the morning and there's a lockdown drill, you have an exam in the afternoon. If you are here all morning and there's no lockdown drill that morning, then we obviously have class, but we're just going to find some more review to do and we will have the exam the next day. So today what we're looking at is called implicit differentiation. And basically we're going to use the method of implicit differentiation to differentiate relations, not functions. Yeah.
Would you be able to send us an email at lunch on Tuesday? Because I'm not here all morning.
Good idea. Absolutely. In case anybody didn't hear what Liam just asked, he asked if I could send an email at lunch on Tuesday to let people know, are we having the exam or not? Because some people aren't here all morning, and that makes perfect sense because if you're out at Buck, you don't know what's going on over here in the morning. So email Tuesday. All right, so implicit differentiation is used to find derivatives of relations. Now, if you've been following, the definitions of relations and functions throughout your high school career, you'll understand that we have been differentiating relations. But usually when we talk about relations and we don't use the word function, we're really talking about relations that are not functions. And remember, conceptually, that a relation is not a function if putting in a single value of x can give you multiple outputs, multiple y's. And that leads to the vertical line test and all of that. By the way, I've always put continue to correctly interpret derivatives as being a method that you can use to find the slope. So we're going to start off with some very basic things, very, very basic. Everything we are differentiating with respect to so far, and will continue to be this way, is x for a while. In a couple weeks, we'll be dealing with differentiating with respect to other variables. So the question is, what is the derivative with respect to x of x? It's not a trick question. If you had x sitting there as part of a question and you had to differentiate it, what is the derivative? Well, the derivative of x is 1, as long as we're differentiating with respect to x. If we were differentiating with respect to t, the derivative of x with respect to t would be 0. Because if the variable is t, then x is a constant, basically. It doesn't depend on the variable. But that's neither here nor there. What is the derivative with respect to x of x squared? Well, again, this is not meant to be a trick question. It's 2x. We would wrap the 2 around the base, which is x. Drop 1 from the exponent, and if you want to be pedantic about it, which means very picky, you then say I'm going to multiply by the derivative with respect to x of what I just wrapped the exponent around. You just wrapped it around x, so now we're back at question A. What's the derivative with respect to x of x? You'd multiply by 1. This is overkill. You don't need to do this when you apply the power rule to a base of x. You don't need to do that. And now the question is this. What if I asked you to differentiate y with respect to x? And I regret telling you a minute ago what I told you about constants. Y is not a constant. Y is a variable. I will never say that again about what I said about the derivative of x with respect to t is 0. It was a mistake. In fact, in the next unit we'll be finding dx dt quite a lot. But the question is, what is the derivative with respect to x of y? And I know what happens. I've asked this question for over 30 years in all of these calculus courses I've taught. And I get all kinds of answers. And usually they're not right. So I know I haven't instilled a whole boatload of confidence in you. And I'm asking you to stick your neck out. But does anybody know what the derivative with respect to x of y is? Arden?
Maybe the derivative of the function of x?
Oh, I like that. It turns out you're right. How would I write that? What Arden said is the derivative with respect to x of y is the derivative of the function of x. And I don't want to put words in your mouth, but is that because y is the function of x? So what should I write? Well, I could write words. I could say it's the derivative of the function of x, but I want to write something with notation. It turns out the answer to this question is something you've been writing over and over and over again. You just haven't been aware. You haven't been conscious of the fact that you're differentiating y with respect to x.
dx over the prime of f.
No. It's dy dx. Exactly, Grant. It's dy dx. And this seems really silly that you're probably saying, well, why is he pointing that out to us? This is kind of like me saying to a grade 10 class, what is this equal to? And the answer is it's equal to root x. You can't write it as a decimal. So Arden kind of hit the nail on the head, and then Grant polished it up by giving us a specific answer. The derivative of y with respect to x is the derivative of y with respect to x. It's dy dx. So I want to pause for a second and point out something that you have actually been differentiating y with respect to x all along. Because I'll give you almost the simplest function I can think of. Well, I'll just give you a function of x. If I said to you in a question, find dy dx, what do you write? You write dy dx equals 33x to the 10, correct? The math is right there, yes? Okay, so when you do something to a mathematical expression to change it, You're operating on it. You're doing something. Maybe you're taking the sine of it. Maybe you're taking the square root of something. Maybe you're multiplying by 2. What we're doing here is we're differentiating with respect to x. We are ddxing the right-hand side of the equation. But if I have this statement, p equals 5, and I say, you know what, I'm going to square the 5, can I get away with writing that? Well, no. If I'm going to square the right-hand side, I have to square the left-hand side. So we've been so fixated and focused on ddxing expressions that have x, we forget that what's happening is we're also ddxing, that's just the way I say it. We've also been differentiating the other side with respect to x. So the derivative with respect to x of y is dy dx. And now the typical response is, okay, so far, so what? The point is now this. What is the derivative with respect to x of y squared? Anybody want to stick their neck out on this one? Zebby? Say that again? Almost. So what Zebby said, and I want to make sure I heard you right, what Zebby said is 2 dy dx, correct? Now, it turns out not quite. And you guys know me, and we're all comfortable with each other. You shouldn't have any problem with me saying, well, that's not right. I mean, that's the whole point of sticking your neck out and trying an answer, is it might be wrong. Makai. And that's another thing that people will say, dy dx quantity squared, and it turns out that's not it either. Liam? A little louder, please. No. dy d of x squared? No. And I don't mean to, put this out here as a hopeless venture that we're just going to spend all this time, but you know how to do this. Y squared is a power. And to differentiate a power, you wrap the... Go ahead.
Maybe 2 times dy dx times x.
No. Makai? Say again? 2y? Oh. If we could somehow marry what you're thinking and what Zebby said... Liam? Or that threw you off the path? No. So let's stop for a second. Do you agree that y squared is a power? And by the way, I'm going to give you the answer. This isn't about you trying to figure it out every time. Once you see the answer, it's kind of obvious. Y squared is a power, so how do you differentiate a power? You wrap the exponent around the base, which stays the same. You drop 1 from the exponent, that's a number 1, and then you multiply by the derivative of what you wrapped the exponent around. But the derivative of what we wrapped the exponent around is dy dx. So the derivative with respect to x of y squared is 2y dy dx. It's the chain rule and the power rule put together. You might ask yourself, among other things like why are we doing this, you might ask yourself, why don't we have to do something like that if I say to you, what is the derivative with respect to x of x squared? Well, we do have to do it. We wrap the 2 around the x, we drop 1 from the exponent, and then we multiply by the derivative of what we wrap the exponent around. But we wrap the exponent around x, and the derivative of x is 1. But if we're wrapping the exponent around y, you have to multiply by the derivative of y, which is not 1. The derivative of y is dy dx. So why do we need to do this? Rather than me going out on a limb and trying to explain to you the usefulness of this, let's just go to an example. Okay. Very briefly, though, I guess I will give you a little bit of an explanation here. In the past, and I've already talked about this, when you're finding a derivative, you've been focusing on the function that has x in it. You haven't been focusing on the other side of the function, which is just written as y. But you actually have been differentiating the y as well. Anytime there's been a y, you've been differentiating it and writing dy dx. When you differentiate, it's important to realize that you're really differentiating both sides of the equation with respect to the independent variable, which is x. Okay? What is implicit differentiation? Implicit differentiation is paying attention to the fact that we're differentiating everything with respect to x. And if you see a y, you change it to dy dx. If you see a y to the 11, you wrap that 11 around the y and write it to the 10, and then multiply by the derivative of y, which is dy dx. So let's take a look at a couple of examples, and hopefully this will explain to you why we need to do this. The thing we want to find the derivative of in example 1 is y squared equals x. Now, if you want to do what we've been doing before, then you need to rearrange that for y. And here's the problem. When you rearrange this for y, which we're not going to do, you end up creating two different functions. You have two different functions. And if you have two different functions creating a single function, and this is kind of a Math 30 thing, you're going to have something that's not a function. To show you the graph of this, this is a parabola laying on its side. So it's not possible to rearrange this into a single y. Is it possible to find dy dx by using two functions and getting two different derivatives? Yes, it is, but one derivative will only work for the top half of that parabola. The other derivative will work for the bottom half. What we want is a derivative that works for any point. So rather than doing this, this is out the window, differentiate this. So we're going to ddx everything. What is the derivative with respect to x of y squared? 2y dy dx. And I really don't write y prime with implicit differentiation. It's going to get very confusing. So what I've done there again, this was part of our warm-up, is I've wrapped the 2 around that base of y. So the new coefficient is 2. The base stays the same, so the base is still y. I've dropped 1 from the exponent, which means it's just y, but if you like, if it helps set your mind at ease, it's y to the 1. Then I multiply by the derivative of what I wrapped the power around. I wrapped the power around y. The derivative of that is dy dx equals 1. Because the derivative with respect to x of x is 1. Now if I differentiate, if I rearrange this for dy dx, it's child's play. It's 1 over 2y. This is interesting. The derivative is not a function of x. The derivative is a function of y. Why should that be the case? This is our answer right here. We're done. But why should that be the case? If I said to you, find the slope of the tangent to this relation at x equals 2, you cannot answer that question. That's a bogus question. It's unanswerable. Because when you look at x equals 2, and let me close some of these off. When you look on that graph at x equals 2, what are we talking about? Mr. Wade, do you want me to find the slope of the tangent here, or do you want me to find it there? And the fact of the matter is, an x coordinate doesn't tell me where the point is on this. But if I gave you a y coordinate, you know exactly what point I'm talking about. And I love this about implicit differentiation. If you need to know a specific point on this, the only thing that's important is the y coordinate. You know the y coordinate, you know which point we're talking about. If I say y equals 1, we're talking about this point right here. No question about it. This is where y equals 1. So because y is the only thing that's important in identifying a point, I think it's kind of cool. The only variable that appears in the derivative is that y variable. You don't need x, you need y. So if I wanted to know the slope of the tangent on this thing where y is 1, I would put y equals 1 in there and I would get 1/2. Are you with me? Okay. Any questions from Buck? Okay, good. I would rather over-explain things here, so be patient. 2x squared minus 2y squared equals 9. Well, you don't learn in Math 30 anymore. We used to teach this. You don't learn how to graph these. And you can't graph it with your graphing calculator because you can't rearrange that for y. Incidentally, the thing that makes it necessary for us to use implicit differentiation is there's a y squared. As soon as there's a y squared, you're dealing with plus or minus when you rearrange for y. In other words, it's not a function. Here's what it looks like. And this is called a hyperbola. And both of those branches, they're kind of like parabolas, but they're not. You can see it's kind of twisted a little bit. Both of these branches extend. I haven't figured out a way to get this graphing program to show this, but they extend in these directions. Now, if I wanted you to know this, to tell me or to figure out the slope of the tangent where x is 5, that wouldn't be enough information, would it? Because when you look where x is 5, I'll go with 4. When x is 4 here and here. There's two different places. So me telling you, well, find the slope of the tangent where x is 4 is kind of it's a bogus question. What if I intended this to be the point here? Why can't I just say find the slope of the tangent when x is 2.5? Because there's another point where x is 2.5 over here. So what do you need to know to locate a point? You need to know both numbers, don't you? Which means the derivative is going to contain an x and a y. It has to. Let's differentiate. What is the derivative with respect to x of 2x squared? 4x. That's it. What we learned a week ago. What is the derivative? So minus, because the derivative of a difference is the difference of the derivatives. What is the derivative of 2y squared? Is the derivative of 2y squared 4y? No, it's 4y dy dx equals, the derivative of 9 is 0. Now I'm going to rearrange for dy dx. That's it. That's all you have to do once you've followed the rules of differentiation. I'm going to move my negative dy dx term to the right-hand side and get 4y dy dx. That just means 4y multiplied by dy dx equals 4x. I can divide both sides now by 4y. Don't forget, I'm trying to get dy dx by itself. I get 4x over 4y. Well, this is really interesting. I find this stuff like this interesting. You don't have to. The derivative is x over y. That's a very interesting, in my mind, mathematical shape. that has these weird arms that go off in both directions, but it turns out any point on there will have a tangent slope equal to the x-coordinate over the y-coordinate. Any questions with example 2? All right, last example. Yeah, it's hard to believe, but we really did used to teach high school students in Math 30-1 how to find out what this thing looks like. It's quite complicated. You have to complete the square of x and complete the square of y at the same time and get two different equations. There are other ways you could do it, like you could plug it into a graphing program, but you can't graph this on your calculator, right? Yeah. The question is, are you allowed to rearrange the equation at the beginning, Ben? Yes, but are we talking, Ben, here maybe about this previous question? Yes, you are, but I would say to you, you're not looking for trouble, but if you rearrange it, it's going to usually become more difficult. Absolutely. Yeah. So what Ben is asking is, could we just do this from the beginning? 2x squared minus 9 equals 2y squared. Are you with me on that, Ben? Definitely. This is actually illustrating something, Ben, and it's that the rule for sums and differences for derivatives of them is that the derivative of a sum is the sum of the derivatives, which means it doesn't matter where the terms are in terms of addition or subtraction. You could certainly do that. What you're going to gain by doing that is when you get 4x squared equals 4y squared dy. When you get 4x equals 4y dy dx, when we differentiated first, then we moved the dy dx term over. If you move the y's over first, you will do that movement first rather than second. Are you kind of with me on what I'm saying, Ben? Okay, good. I was very cautious in answering that because I don't think you want to start getting in the habit of saying, I want to get y by itself, because getting y by itself is really a non-starter. And I know you know that. Okay, so let's take a look at this one. Well, what does this look like? It's called an ellipse. Oh no, it's another hyperbola. But it's really, really twisted. And again, what we are looking at here is a graph whose point anywhere on the graph would have to be defined by both x and y. You'd have to know the x and the y value to say it's, this point or this point. So let's differentiate it. And this isn't, well, there's a bit of work here. We've done more challenging work than this. You just have to follow the rules. So what is the derivative of x squared? Well, it's a power. This is a power. So we use the power rule. We wrap the exponent around the x and drop 1 from the exponent. And if you want to be picky, we now multiply by the derivative of what we wrap the exponent around. But we just wrap the exponent around x. And the derivative of x with respect to x is 1, so we don't need to do that. Then we have plus. This is a product. I know that everybody in the room will be tempted when you differentiate 2xy to do something like this. Because you'll say, well, the derivative of x is 1 and the derivative of y is dy dx. But that's not how you find the derivative of a product. You have to use the product rule. So that product, right now we're talking about the derivative with respect to x of 2xy. That's what we're talking about writing down next, is found by taking the derivative of the first times the second plus the first times the derivative of the second. And I think it's wise to take that coefficient of 2 and tie it to something. tie it to the x. So the derivative of 2x, which is the first, is 2 times the second, which is y, plus the first, which is 2x, times the derivative of the second, which is dy dx. And I don't mean to clutter up the workspace here, but I want to make sure that you understand, whether you're watching this on video later or you're with me here. This is the derivative of the first. This is the second. This is the first. This is the derivative of the second. If you want that in your notes, you can do that. I'm about to erase it. The math in that step that I've just done is not difficult, but it requires thought. You can't be impulsive here and just start, wrapping exponents around things without thought to what it is you're doing. What do we have then? Then we have another power. And we have minus the power. So the difference law says if you're subtracting something, then you can just subtract the derivative. So I have a power of 2y squared. So what is the derivative with respect to x of 2 times a variable raised to an exponent? Well, it's found by wrapping that 2 around the variable, or the base, rewriting the base exactly the way it is and dropping 1 from the exponent, and then multiplying by the derivative of the base, which would be dy dx. All that's happening here on the right-hand side, which again I'm going to erase in a second, is me explaining why I'm going to write minus 4y dy dx. I'm wrapping the exponent around the 2y squared, so it becomes 4y to the 1. Then I'm multiplying by the derivative of y, which is dy dx. Then we have minus 2x, and I think I can dispense with all of the explanations on the side now. This is just, well, I don't know what I want to, I guess it's a power, right? It is a power, 2x to the 1. I wrap the 1 around the x, it becomes 2x to the 0, which is 2. So it's minus 2. I guess technically this is a power as well. I'm going to wrap that exponent of 1 around the base and get 1y to the 0. But then I have to multiply by the derivative of the base that I wrapped the power around, or the exponent around, which is dy dx. I kind of think that's really overkill. It's y. What's the derivative of y? Dy dx. Minus the derivative of 54, which is 0, and this is equal to the derivative of 0, which is also 0. So going from the beginning, the derivative of x squared is definitely 2x. The derivative of 2xy, thinking of 2xy as 2x times y, where 2x is the first. The derivative of 2x is 2 times y is the second, plus the first, which is 2x, times the derivative of y, which is dy dx. Then minus the derivative of 2y squared. Wrap the 2 around the 2y, around the y, to get 4y to the 1 times the derivative of y. In case you hasn't dawned on you, anytime you differentiate a term that's y-oriented, you have to follow it up with dy dx. Minus the derivative of 2x, which is 2, plus the derivative of y, which is dy dx, minus 0 equals 0. So are we okay with does anybody have any questions about any of those pieces? Now, I have to give this analogy, even though if you're in Math 30-1, it will be lost on you because you haven't taken it. How many of you remember when we were solving logarithmic equations, and we would have multiple terms that have x in them, and we'd have to move all those terms to one side and all the numbers to the other side. And then when we did that, the only way to get the x by itself was to factor it out. That's what we have to do here with the dy dx's. You have to move the dy dx's to one side of this equation and the non-dy dx's to the other side. And we have 6 terms. As a general rule, I don't want to spend too much time on this. Holy smokes. As a general rule, you want to move stuff to the sides that gives you fewer negatives. But I don't think it really matters here. For example, if we leave the dy dx's alone, I have this. And if I move the non-dy dx terms to the other side, I get 2 minus 2x minus 2y. So I end up here with, I guess, 3 negatives. I think if I moved stuff to the opposite sides, I'd still have 3 negatives. Because the 1 negative dy dx would turn into 2 negative, and the 2 negative non-dy dx's would turn into 1 negative. Anyway, the only way for you to get that dy dx is to extract it by factoring. Factor that dy dx out, and we will have 2x minus 4y plus 1 as the other factor equals 2 minus 2x minus 2y, and then just divide by the 2x minus 4y plus 1, and you have your answer. So the derivative of this relation will be 2 minus 2x minus 2y over 2x minus 4y plus 1. You cannot cancel anything because there's no factors to be found there. Go ahead, Evan. That's a good question because I've already gone on record as saying the more factoring that can be done is better. The question that Evan is asking is, even though it doesn't lead anywhere, should we do this? And the answer is you don't have to. It's a wise thing to look at because, as we'll see with a monster of a question tomorrow, sometimes it does lead you somewhere that's not obvious until you do it. One of the reasons why you want things factored is you want to be able to determine where the numerator equals 0. So if you did have to do that, then in the process you would factor out the 2 anyway. So it doesn't really matter that much here. By the way, if you decide to move stuff to the opposite sides, I'm sure this is obvious to many of you, if you decide to move stuff to the opposite sides, and I'm going to go with this, what you will get instead is 2x plus 2y minus 2 over 4y minus 2x minus 1. Every single term on the top and on the bottom of this will be opposite. That's all. And I say that because you're going to do some of these questions. Then you'll look in the back and you'll go, what? It's just that the author may have decided to move stuff to the opposite side. So that's really it. When you're doing implicit differentiation, you're differentiating everything with respect to x, and that means everything including y's. As rearranging goes, Ben, I wouldn't worry too much about it. Usually, you can rearrange first a little bit if you want, but be careful about rearranging too much. All right, so I will let everybody get to work here. Yeah, get to work. By the way, this is one I might rearrange first. I think it might be easier to differentiate that than it is to use the quotient rule. Anyway, I'll let you get to work. Demi, Nicole, and Zach, were you given your next assignment? Okay. And I'm going to give everybody here your next assignment, which is due Friday. You should be able to do, it's got 3 questions on it. You should be able to do the first 2, and then you'll be able to do the next one tomorrow. Ben, do you want me to email your assignment to you? Okay, I'll do that.